In this video, we are going to talk about sign extension for 2's complement numbers. Okay, so let's start with what sign extension means. Let's say you have a number, I'm going to write, for example, 1101, and you have another number 0010. These are both 2's complement 4-bit numbers, right? They have some value. And we want to represent the same value that these numbers have instead of 4-bit, now in, let's say, 8 bits. How can we represent the same number that we have here in 8 bits? For the positive value, it should be obvious. You just add 4 bits and that's all you have to do. How about the negative value? How can I sign extend it? How can I extend it to 8 bits? The answer is you sign extend it, meaning that you get that sign bit and you just keep repeating that. So you just add ones. So in this case, in both cases, you're just looking at the most significant bit. Whatever the value of that most significant bit was, you just keep repeating it. And that's what we call sign extension. Sign extension allows you to make a number longer. So if it's 4-bit, you can make it 8 bits. Okay, so that sounds good. We can do examples to see that it works. But instead of doing that, I want to do a very quick proof of why this procedure is correct. Okay, so let's look at the proof. The setting we are going to use is this. Let's say you have your two numbers. You have one number A with n bits, so 0 to n minus 1. You have sign extended that number to get another number B, which is going to have m bits. So B is the sign extension of A. What does that mean? It means that A0 equals to B0, A1 equals to B1, all the way to Bn minus 1. And then Bn minus 1 equals to Bn. So all these digits are equal to each other. This is equal to An minus 1. And all these other bits are pairwise equal with one another. Okay, so that's the setting that we have. Now we want to prove the equivalency of these two numbers in decimal. Okay, so what I'm going to do is I'm going to write the decimal number for A. Remember from this second property that we proved, A is minus 2 n minus 1, A n minus 1 plus the sum from 0 to n minus 2 of 2i ai. Now, I'm going to write here for myself also what B is. B is going to be very simple, minus 2m minus 1, bm minus 1, plus the sum from 0 to m. We want to get from this quantity here to that quantity. Let's see how we can manage to do that. The first thing that you should notice is that the A's can be replaced with a B. Right, so all these A's that we have here, all the n minus 2 ones, we said they're equivalent to B, so I can just replace them. So I'm going to just rewrite this. And I can do the same thing for A n minus 1 as well. Okay, so now things look a little bit nicer. 2i bi. Now I need to get to m minus 2. I have n minus 2 here. So let me just take this sum and rewrite it as follows. I'm copying the first term. That first term I'm going to write as the sum from 0 to m minus 2 of 2i bi minus the sum from n minus 1 to m minus 2 of 2i bi. You should be able to convince yourself that this term equals this term, right? Because we are summing over here all the way to m minus 2. but then we are subtracting all the terms from n minus 1 to n minus 2. They are going to cancel each other out, and you're going to be left with terms from 0 to n minus 2. Okay, so far so good. We have a lot of elements that we are going to need, right? So if you look at it, we have this element here, which is exactly this. So we can, we don't have to worry too much about that term anymore. Okay, so the next step is I'm going to note one very simple thing. If you look at these BIs here, their indices are all between n minus 1 and n minus 2. So they're in this range. And all of those are equal to this most significant one, bm minus 1. Sorry, I had forgotten m minus 1 here. I just fixed that. Okay, so they are all equal to they are all equal to each other. So I'm going to replace all of them with bm minus 1. So what you will be left with is that term over there equals to, I'm going to write minus bm minus 1. You have a 2n minus 1. That comes from this term right here. And then I'm going to write this ones as well. So these BIs are all bm minus 1, so they come out of the sum. And I'm factoring them out with this minus, so you just get this sum inside. Okay, so you can convince yourself that if you multiply this by this, you get the same thing. The reason is that all the BIs are equal to bm minus 1 in that range that we are looking at here. And that yellow term, we just have to take that and paste it here again. So I just did that. That yellow term, I just copy paste that. Right, I just carried it over. Very good. So now we are getting very close to what we want. We have this term versus this term. So I want to quickly remind you of an equation that we have seen several times by now. 2 to the power of x is equal to sum from 0 to x minus 1 of 2 to the I, the whole thing, plus 1. We have seen this over and over again. So what I'm going to do now is write this term over here. I'm going to write this as 2n minus 1 plus sum from 0 to n minus 2 to the I minus sum from n minus 2 from 0 to n minus 2 of 2 to the I. So just note what I did here. I took this term over here and I replaced it with this. Right, we have one sum, which I have written as a sum that starts with index 0. But the first n minus 2 ones I'm removing afterward. Why did I do this silly thing? Well, because we wanted to be able to use this equation to get rid of all these sums, right? And in this equation, the index starts from 0. So I'm now going to simply just plug in that equation for both of these sums. Okay, so the first sum is going to be 2 to the m minus 1 minus 1. And then the second one is going to be 2 to the n minus 1 minus 1. Close parentheses. Let me copy all these other terms as well. Okay, that's great. So now things work rather well, because if you look at this 2n minus 1 gets cancelled with this minus 2n minus 1, and this minus 1 gets cancelled with this minus minus 1, and you are left with 2 to the n minus 1. So what you have at the end is minus b 2 to the n minus 1 plus some plus that yellow term, which I'm going to paste exactly again. And that completes the proof. That completes our discussion on sign extension. And in fact, on two's complement, in the next sessions, we will start to learn about hardware design for adders.